Hello, good morning. Just want to start by saying thank you very much for the opportunity to be here today. While this is the first summit that I've been to, I know Johnson Controls has been partnered to this summit since its inception, and I can certainly see why. From the conversations that I've had out in the corridor to the presentations I've seen today, really clearly an exchange of best practices, thought leadership concepts, and obviously a focus on innovation. So hopefully with this next 20 minutes we can share another topic that helps advance kind of that mission and that thinking. I think just sort of to tee this up a little bit, energy storage, I think fundamentally if you look at how we procure energy and use energy in the United States, there's just a natural inefficiency with the commodity of energy that comes from the fact that it nearly needs to be consumed and manufactured almost instantaneously. And so we're excited to share with you energy storage and how it can help change the needle and move the needle a little bit on that kind of topic. So at the end of this, I hope that you recognize the opportunities for energy storage to provide economic value to your facility, to help advance distributed energy systems, particularly renewables, and also how it can help play a role in advancing microgrids. Obviously, that's a hot topic, energy resiliency, those kinds of concepts, and so energy storage really is a kind of a linchpin in providing that. Just quick introductions. My name is Jeremy Neiderjohn. I'm responsible for kind of the business side of the distributed energy storage practice at Johnson Controls. I suspect that many of you may know Johnson Controls from doing energy efficiency, performance contracting. We manufacture mechanical equipment controls, things like that. But the other big chunk of the business is that we're one of the largest battery manufacturers in the world. So the team that I'm a part of is kind of a nice marriage of those two organizations. And also with me is Curtis Fox. Curtis is the Director of Operations for the Energy Innovation Center at Clemson University. And we've been working a lot together over the last year. And so what we wanted to do is just sort of frame energy storage, talk about what it is, what you do with it, a little bit around the market for energy storage. And then Curtis will add some thoughts too about, practically his experiences with deploying it and some of the considerations that have gone into it. So this chart here is taken from a document by the Rocky Mountain Institute. It's a really well done piece if you have an opportunity to read it. But I wanted to just start with an understanding of what do you do with energy storage? What kind of value does it provide? And I suspect that in the room here, there's a level of familiarity with energy storage, but that there's some variance in really the depth of understanding. So really wanted to start with kind of what do you do with it? The classic example that I think everybody's probably most familiar with is doing demand charge management. So charging up a battery, using some controls to understand and predict when a peak is going to occur, and then deploying the battery to shave the peak. For a lot of our clients, there's significant costs associated with demand charge savings. In fact, listening to some of the discussion and presentations earlier, I think largely people expect demand charges to continue to rise. So there's certainly a lot of value in doing that, and that's the way a lot of energy storage has been deployed today. It can also, kind of the corollary to that is it can affect the KWH piece of the bill. If you have an opportunity to have different pricing with respect to your energy purchasing, you can, again, buy low and utilize the asset when energy is more expensive. Energy storage can also participate in ancillary services markets where they are available. So today, there's been a robust ancillary services market in PJM, kind of the northeast part of the country, and particular frequency regulation. So frequency regulation is a service to help the grid. It's provided on the behind the meter or the building side, but it helps the grid balance supply and demand at any given time and manage frequency. And so a battery is a really good asset for doing that because it can almost instantaneously either charge if there's oversupply or provide power if there's demand needs. Energy storage is always partnered with an inverter, and those inverters are nearly always 4-quadrant inverters. So for clients that have power factor challenges, it's a good resource for doing that. Almost every customer has some interest in backup power, and I think the thing that's unique, there's certainly nothing unique about using an energy storage device to provide backup power, but I think what can be a little bit unique is the ability to monetize that asset, participating in other markets, doing demand charge management, things like that, and also have that asset have some capacity at the bottom to provide backup power. Demand response, it's a great asset for providing demand response, particularly for clients that might have demand response fatigue. We've got a number of clients that have that, where it's just, you can't make the changes if demand response events are being called that often. And it also allows you to participate in demand response programs without really any impact to the facility. Renewable energy support. Anytime that renewable energies are being considered, particularly solar PV, is a great time to consider energy storage. And there's a few reasons. One of them is just the ability to manage kind of the slope of the output of the PV. So a cloud goes over, you drop the PV pretty quickly, cloud goes away, it ramps up pretty quickly. Energy storage is great for kind of managing that. It also can provide a backstop on demand charges. And then the final piece is that if you have, if you have a lot of roof space, put PV up there, and the output exceeds the demand of the building at any given time, you can put it in the battery and effectively extend daylight hours into nighttime. And then the final one is microgrids. It's a key piece of a microgrid. So the market for energy storage, really being driven by North America and the United States today, and as we'll talk about in the next slide, California in general, but see significant growth. So this is an industry that is absolutely emerging. And I think the things that are most important about this and what will drive the growth are really two big things. I think by and large, there's an expectation that energy and demand charges aren't going down. They're going up. I think there's some debate on what that slope looks like, but generally believe they're going up. And the other variable that's very important is the decreasing cost of the systems. So there's lots of different energy storage technologies. Not going to get into all of that in this presentation with the time. However, it is largely a battery-driven market, and because of the scale in manufacturing around lithium-ion, it has been predominantly a lithium-ion driven market as well. And so that scale continues to come down and the cost curves continue to change, and the costs are changing rapidly, and that really helps enable additional markets. So if you look at the segmentation a little bit, no question California's led the way. It's the perfect storm of high demand charges, high penetration of renewables. They have an incentive in place. They have a goal that they're trying to meet. So California has been the leader. But there are lots of other markets that are particularly attractive as well. PJM talked about that from a frequency regulation perspective. New York, a speaker earlier talked about New York REV. Energy storage is part and parcel to that. Markets like Texas, New England, the Pacific Northwest, even MISO in the middle of the country has talked about implementing a ancillary services market in a kind of a deregulated sense. So lots of increasing opportunity. What do these solutions look like? You can see up here, basically, this just happens to be ours, but they're all very similar. It's a indoor. There's often an indoor application that's smaller kilowatt hours. In this case, it's in the 60 to 100 kilowatt hours kind of range. And then there's containerized systems, which can be half megawatt hour, 1.5, multi-megawatt hour kinds of systems. So depending on the application, the building size, what you're looking to do with it, you sort of put the parts and pieces to really help meet the requirements. So I talked a little bit about the things that you do with an energy storage system. And I think it's important, in particular for the audience here, that's really focused on behind-the-meter, distributed, building kinds of systems, to understand how that energy storage system sort of fits within a facility. So if you think about all of the different assets, energy-consuming assets in the facility, and you think about doing something like demand charge management, you could certainly put in a battery to do that, But where you get a whole lot more economic value is when you control that battery in conjunction with all the other stuff in the building. So if you're thinking about, shaving a peak, using a battery to do, a good chunk of that shaving, but also maybe pre-cool the building, and a lot of the things that I'm sure you're doing anyways, but doing them all coordinated and in concert. And then along with that, having some technology that allows the battery, where applicable, to participate in grid-related markets. So when you throw all of these things that a battery could do in a bowl, and you sort of mix it up, what's important is to have some level of controls that say, the most effective thing that the battery can do is perform demand management tomorrow. It's going to be a peak day. We want to make sure everything we're doing is focused on shaving that peak. However, it's another time of the year where that's unlikely to be the case. Have it be smart enough to understand and make the trade-offs between doing that function and doing something else to provide the most economic value for your facility. So with that, turn it over to Curtis and let him talk a little bit about some of the learnings he's had about deploying these systems.
Okay, thank you, Jeremy. Just a little bit of background of where Clemson and Johnson Controls started this process and kind of why Clemson's involved in this. We have a satellite campus in Charleston, South Carolina, where we have multi-megawatt wind turbine and energy storage and solar energy test facilities. So we have a 15 megawatt and a 7.5 megawatt wind turbine dynamometer. We test the full-scale turbine. We take the blades off, we take the tower off, but we push on it like the blades would and do a lot of work associated with that. We also do a lot of work in the solar arena. We're talking more of your utility scale solar. And then Johnson Controls was also one of the partners that came in to look at this energy storage asset. And so how this relationship evolved and developed was we had a facility that was capable of testing not just the energy storage capability, but also its capability under different use cases, different energy power requirements, ancillary services, fault ride through, those types of things. So we worked with Johnson Controls to put together basically a customized test plan to look at and validate this energy storage system. When Jeremy showed you those things, this particular system that we validated was a 510 kilowatt hour containerized solution with a 1 megawatt inverter to it. And so it was really just to take that system through its paces in the lab and develop some concepts about it. And what I'd like to, or some data-driven analysis of that system, and what I'd like to do is kind of share with you a little bit of the, where the marketplace is in energy storage and where the actual, the future may lie, and some things to look out if you are thinking about energy storage. Give you some idea of questions to ask vendors. So basically, if we look at the energy storage landscape, Jeremy mentioned it already, prices are coming down. What a lot of people have done is third-party integrators have tried to use batteries and inverters like a commodity. The problem is that all these systems need to operate together. There's several layers of hierarchical control within this system that need to coordinate. And one of the biggest challenges with multiple vendors is you're dealing with multiple vendors. Even if the top integrator, believes they're going to be integrating an end-to-end solution, invariably you end up with people pointing fingers. So there's very few actual companies out there that take the whole integration under their purview, under a project, and most of them are actually being led by the battery manufacturers. Some of the other challenges out there is comparing a system from vendor A to a system from vendor B. Okay, you've got an energy capacity rating, you've got a power rating with your inverter, you've got efficiencies you need to look at. So understanding the actual use case of the system prior to doing this, not just assuming that you can stack value streams, will actually allow you to develop a more realistic project around these types of things. There's been several efforts to kind of develop protocols for validating and testing energy storage systems, but the problem is that the use cases that Jeremy showed you earlier, some of them are very power dependent, some of them are very energy dependent, some of them kind of fall in between. And so you can run into issues associated with actually stacking those value streams if one is heavily energy dependent and the other one's heavily power dependent. And so in doing this with Johnson Controls, we're able to adjust a number of things and evaluate the battery system under many different use cases. But the biggest thing I'd say is there's a lot of, the technology is still maturing, okay? And the market is not even keeping up with the technology growth rate. So there's things that just aren't available in today's market, but that could be taken advantage of in future energy storage. But energy storage is in a nice, unique application that it's out in front of the market, so it has time to develop the technology to actually meet these use cases. And my final bullet point there is there's no value stream unless it actually really works, okay? One of the biggest things that we see with energy storage systems, PV systems are somewhat the same way as well, is that manufacturers like to quote a single number for efficiency. That is farther from the point than I could even imagine. Through testing and evaluation and understanding, you need to get a really good concept of how this system works efficiently over the full range of charging and discharging. The charging efficiency, the discharging efficiency, those are going to be different. They're going to depend upon the rate in which you do them, the power level in which you're running, and the inverter and the batteries actually have to be well matched. I mean, you wouldn't necessarily go and buy a car chassis from one manufacturer and then throw another engine in it. You wouldn't assume that risk, and so it's really a marriage in a package system that needs to be developed. But by looking at efficiency of the system, you can start weighing cost functions of these different revenue streams, okay, and really evaluate the performance realistically of what the system's going to look like if you try and do you try and do demand charge management and energy arbitrage at the same time. You need to have a really clear view of what are your losses going to be. And you don't want to drain your battery to keep it running at very low efficiency levels. The other thing about efficiencies and those types of things is when you monitor them and you track them continuously and online, it allows you to also begin using them in your control algorithms. You understand that this is going to be a cost metric that you're going to have to deal with, and there's going to be a penalty to the energy you have available in your battery if you participate in A, B, or C, and you can better understand that. And the other thing is you can begin to use these numbers for asset health management. A containerized solution may have thousands, tens of thousands of batteries in it, okay? And by understanding the data-driven analysis here, you can begin to predict what the failure rate may be, begin to identify modules or cells that you want to change. So there's a lot of things that need to be accounted for. And in maturing markets like this, the consumer needs to be educated as to specifically what they're looking for. One application where efficiency is really kind of unique is, Jeremy mentioned frequency regulation in PJM, okay? And frequency regulation is where you try and, with fast responding resources like energy storage, it can respond to 0 to whatever is rated power within a couple cycles of 60 hertz. So very, very fast response rates. And so frequency regulation, it tries to be the middleman, the buffer between generation and demand, and basically level it out such that the frequency on the system stays near 60 hertz. So it's constantly pushing and pulling and pushing and pulling energy to keep the system as stable as possible. And you look at the frequency demand market, you get paid on what your maximum power capability to deliver is. Okay, so you don't really need a whole lot of energy, you need a lot of power. But what's a misnomer about it is that you actually, because you're constantly pushing and pulling, okay, you're going back and forth from charge to discharge, you actually spend a significant amount of time around zero power. And what that means is that you actually operate this system in an area where it's very inefficient a lot of the time. And so if you don't take this into account, these types of things into account, with data-driven models and data-driven analysis, you can possibly fall on your face and not actually get the response out of the system that you're expecting. And then the other thing about data-driven analysis and control algorithm development is, it need not be overly complex. We don't have to have, computational fluid dynamics and FEA analysis of everything. Data-driven models in this type of market, in this type of complex system, are the most efficient way to determine how your system's operating. And they can be almost algebraic models or exponential models, and you can get really good prediction out of them. Okay? And so with that, I'll hand it back over to Jeremy here.
Yeah. So thank you very much. We're excited to keep talking about it. We've been told that to keep things on pace. However, there won't be questions, but we'll be around certainly for a bit today, and we'd love to talk to people about it. So thanks very much for the time and the opportunity to speak today.